04. Excuse me, 03. Different optimal solutions in shared path graphs. And we have Goldner, Department of Mathematics, Ohio College, and S. McCulloch, Department of Mathematics and Computer Science, Ohio Wesleyan, and the presenter is Kira Goldner.
I'm Kira Goldner. I'm from Oberlin College, though I'm doing research with Ohio Wesleyan's REU. Sean McCulloch is my mentor, and I'm doing different optimal solutions in shared path graphs. So some basic graph theory for you. If you've got a bunch of dots, these are called vertices, and then you connect them in some way. Those are edges. This is the basic graph. Then you add edge costs to them. What this is how much you have to pay to use any one of these edges, and this is called a weighted graph. A connected graph means that every vertex has at least one path to any other vertex, not necessarily directly. And then we have journeys, which are, if you have a point A and a point B in mind and you want to get from point A to point B, that's what a journey is. So for example, green is going from 0 to 3. Now the path is the actual sequence of edges it's taking, so green's path would be 0 to 1 to 2 to 3. So the classic problem, as some of you may know, the shortest path in graph problem concerns finding the least cost paths for journeys in a weighted connected graph. Dijkstra's algorithm is a solution that finds this for you. As you can see on the left, they're all routed by their shortest paths. You know that green is the shortest because it's going 0, 1 to 2 to 3, which costs 7. Whereas if it were to go 0 to 4 to 2 to 3, it would cost 10, 7 plus 1 plus 2. However, our twist to the problem is we allow journeys to equally split the cost of any edges that they have in common between them. And what happens here is it gives them incentives to take different routes because then they can share the edges. So for example, on the graph at the right, it's the exact same graph. However, here we're allowing sharing. So green has the incentive to take a different route. Here you can see as green goes from 0 to 4, instead of paying 7 as it would have before, it pays 3.5 because it splits it with red. And when it goes from 4 to 2 to 3, instead of paying 3, it pays 1.5 because it splits it with yellow. So here green only costs 5, which is way shorter than its original shortest path. However, if we define total resources to be the sum of all of the costs of journeys in a graph, then in a normal shortest path graph, unshared, you have that minimizing the total resources is the exact same as minimizing the individual paths. However, in a shared path graph, you might have one journey have a longer individual path because it'll go out of its way to share edges with other journeys, reducing their costs and thus reducing the total resources. So you need to define what is optimal, what you're looking for. So my work has mostly been in looking into different optimality conditions in graphs and solving for that in shared graphs. So the first one is minimizing total resources. You can kind of think of this as telephone wiring. If the vertices are telephone poles and the edges are wires, the government's paying for all of the wiring. They don't care how long it takes for one individual path to go. They just want to minimize the total resources because they're paying for all of it. The second application is sort of inherently selfish beings. So if you imagine us, we all want to save gas in this economy. And then you let us carpool so that we can save even more gas. However, still, no one's going to go out of their way to carpool with someone if it means that they have to spend more. And the third one, which I had to add because I'm from Oberlin and in the cooperative spirit we have, is the cooperative solutions, which means that it's kind of like the second application, but you're having the government step in maybe and say, I want to reduce the maximum cost that any individual has to pay. I want to bring down the outlying journeys. So a heuristic, as you may know, is not an actual solution. It's pretty close. It's an approximation, like the picture on the right. And so I developed heuristics, and in past work, they developed heuristics too. The past heuristics mostly focused on minimizing total resources, although they didn't really set their definitions of optimality, so it crossed over a little bit too. So some game theory basics for you. This works for the second definition of optimality. The first assumption is that journeys are inherently selfish. They don't care about minimizing the total resources in a graph. They don't care about how poorly the other journeys are doing. They just want to minimize their own path, their own costs at any cost. So a concept of this is a strong Nash equilibrium. And what this means is, given how everyone else is behaving, if a bunch of us get together, a group of size anywhere from 1 to however many of us there are, we can't change our strategy to make everyone in our group do better. So if you all are currently routed in some way and we all get together and we say, hey, if we all change our strategy at the exact same time and every single one of us improves, we're going to do it, even if it screws them all over. So if no one can do that, no group can form, then you're in a strong Nash equilibrium. And the reason this is good is because it's the epitome of stability. What this means is if you have this in a graph, no one really has any incentive to move. So if you're looking at the way people might travel on a highway system by this, you could say, or how people might carpool, you can make a highway system depending on this. The third thing is that strong Nash equilibria don't exist in every graph, as I'll show you in a minute. and also determining whether they exist and finding them if they do exist are both suspected to be NP-complete problems. So this is an example of a strong Nash equilibrium not existing because the groups can gang up to change. So as you see in the upper left graph, red's currently costing 3, yellow 4, and blue 5. If blue and yellow decide to strategize together and move based on how red already is, they realize if they change their formation at the same time, then they can both do better, so they will. So that's what we have at the upper right. And then it'll keep defecting because coalitions can keep forming and ganging up together to change their strategies for the better, which shows that since it's in a cycle of nonstop defections, that means that there is no strong Nash equilibrium. So the strong Nash equilibria, or SNE heuristic that I developed, basically checks to see if there are strong Nash equilibria and finds them if there are, finds one. So the way it works is that we check every possible coalition. That means if there are 10 journeys on a graph, we check every coalition of size 9, 8, 7, et cetera. And we say, hey, given how everyone else is behaving, because we need to sort of account for the non-coalition members and the way we can share with them, given how they're behaving, how can we reroute over it? And if we can reroute over it so that every single one of us improves, we'll keep the change. Otherwise, no one would join the group if they didn't improve, so they won't join the group and it won't commit the change. So you can see this happening in this again, because we'll check every possible coalition in the upper left graph. We'll say, red and yellow, do you want to move? And they'll say, no, we're good, thanks. Then you'll say, red and blue, do you want to move? And blue will say, you know what, I do want to move, but red will say, I'm good, I don't want to move, so they won't form the coalition. And then blue and yellow, do you want to move? They do want to move, so they defect. So there are 3 possible outcomes. The first is that in our giant loop around this, if it never ever changes, no coalitions ever want to move, that means that the graph is already in an SNE. The second outcome is that it might change for a while, the graph will be defecting, but then it will stop defecting and not defect again, which means we found an SNE. And the third outcome is that it is in a cycle of nonstop defections, as we just showed, and that means that none can be found. However, there's an issue with this because in the actual coding, it only checks the last loop of it. It can't actually check for how long it's been going and then it stops because of the way that the loop depends on the number of journeys. So of course, with everything, we have complications. The first is, as you may have noticed, there are 2 to the n coalitions we'd have to check every single one. So that's 10 choose 9 plus 10 choose 8. That's a lot, which means that for 10 journeys or 15 journeys, this program could take days to run. The second thing is the optimal rerouting of the coalition. When we say, coalition, do you want to move? Can you reroute in a better way? We're using pre-existing heuristics to do this. And since those are only heuristics in and of themselves, this can only be a heuristic. The third thing is that when we consider non-coalition members and the way we can share with them, it's a little bit wonky, the way the coding works. And the third is the 3 outcomes. As I said, you can only check the final loop to see if it moves. So for example, if the graph might defect if it had one more loop, we may think we found a strong Nash equilibrium when there isn't actually one. So the question that I explored was, what if we compared this full 2 to the n coalitions exhaustive solution to a speedy version where we only check coalition sizes of 3 and 2, pairs and trios? And what I did was I ran 100 tests. In every test, we have 100 different graphs that start from 4 different starting formations. That's the way it is. And out of all 400 of those different formations that we checked, there were only 4 mismatches where the speedy version didn't find the exact same solution as the exhaustive version. So that's pretty good. Also, there are obviously imperfect outcomes because this is a heuristic. So then the third definition is cooperative journeys. The concept is that we want to minimize the maximum amount that any journey has to pay. The idea came from this graph. As you can see on the left, the journeys go from 0 to 4 and 1 to 5. And with any of our pre-existing heuristics, when we route it, it always ends up where orange is paying 5 and green is paying 9. And that's just not fair, because as you can see at the right, if they go through the middle, they each pay 7, which is a lot more equal. The maximum cost goes from 9 to 7, and it's just cooperative. So what I did was I developed a heuristic to find this formation in a graph and try and find cooperative solutions in graphs. What it does is it looks through every edge on a graph. If the edge is shared, if there's more than one journey on it, it momentarily deletes the edge. Then it reroutes the journeys that formerly used the edge. If the maximum journey cost has improved, so if the maximum cost that any individual journey pays goes down, then it keeps that formation, otherwise it goes back to the way it was before. So I did the same 100 tests on this too. However, the biggest issue is that there's no way to compare. We don't have the ideal cooperative solution in mind, so we can't tell if this heuristic is actually giving us the most cooperative solution. Also, there were a lack of trends. I was looking for which pre-existing heuristics were closest to the cooperative solution already, and there was a general lack of trends. Out of the 100 different graphs, 18 of those graphs within the 4 different starting formations achieved different results where they didn't all come up with the exact same solution. If this were a perfect heuristic, they should all come up with the same solution. However, I did notice a correlation between those 18 where the results were different and also graphs where strong Nash equilibria were said to not exist. Continuing work in the future, I'd like to make improvements to the heuristics, working on the outcomes in the strong Nash equilibria heuristic and improving the cooperative one in general. Also, I said SNE existence is an NP-complete problem, or is suspected to be. However, if we study graphs where SNEs do exist, we can look for conditions that are always present and hopefully determine existence faster. If we compare different strong Nash equilibria, oftentimes graphs have multiple in one graph. And it would be great to sort of measure which is more stable. And also the order of steps of deletion, like in the cooperative algorithm where we delete edges because the order has an impact on the outcome. So the conclusion is that using shared paths, we can find solutions for given graphs and journeys that meet different definitions of optimal. Thank you. Any questions?
Questions for
Ben?
So in the selfish model, if like if I'm red and blue wants to form a coalition with me, but it would cost more for me to do that, even though it would reduce the total resources, I wouldn't do it. So what if it didn't affect me? Like I would use the same amount, but I would have to reroute.
That's actually something that I have on my list of things to look into in the future. Currently, it's a strictly only if you improve because, but I was looking into maybe how many people shared each edge to look into a second degree of stability. So if less people share an edge, that means there's less of a chance for people to screw you over. So maybe looking into that. But currently, right now, it's just strictly only if you improve.
On your slide about 3 outcomes, where the last one said no SNE found,
Right.
does that mean that there isn't one, or you just didn't find it?
Well, if it worked perfectly, it would mean there isn't one. It would mean it was stuck in a cycle of defections. But because when we looked to see if one is found or not, we're only checking the last loop around the whole heuristic. That just means that it changed with the last loop. It never stopped changing. So we assume it's stuck in a cycle, but there may actually still be one because it's just a heuristic. So that's why you say found. Yeah?
You implied that you might look for necessary conditions for an equilibrium, kind of at the end here. Is there any hope at all for finding a sufficient condition where you just are looking at a graph and you can say ahead of time if equilibrium exists?
I think it would take a lot of analysis. I spent a couple days on it at the very beginning of the program and didn't really have any success with it, but I don't know. Yeah?
So if you're analyzing, say, like 8 possible coalitions, and you find that coalitions like 3 and 5 would both improve, but they're mutually exclusive, how do you pick one?
So the way that this is kind of what I was talking about at the end with focusing on the order of how things are chosen and how they have an impact. The way it currently works is we check for larger coalitions first, because if more people can improve, then they might want to. But so we go in sort of an arbitrary order based on how the journeys are listed in the graph in larger sizes to smaller sizes. But that does have an impact.
So it might be possible like several smaller coalitions rather than one large coalition.
Exactly. Anybody else?
Okay, let's thank